Hmm. I feel... hmm. I feel very conflicted as to which one of these I should use. This one is reliable, but this one is compact. hmm. This one is also faster. Hmm. Need to remember where these two pins are. And... wait. Difficult to see the wiring because it's all inline. Here. Where? Hmm. Oh yes, now I remember how I did this one. Oh yes, now I remember. This can't be consolidated into a single one like this because it's connected to each one of these conditionally. Very small improvement. But not unwelcome. I'm only going to make a temporary copy of this so that I can just glue them together quickly. There. And now we only need the last one, which I think is technically redundant. But you definitely don't want to wire the input to all of these every time. And so compromising speed for an abstraction layer so that you don't go insane wiring 50,000 things to each other. There. And then these are irrelevant. And this is the revised version. Actually, I'd like to replace it. So that's the name. That seems like a good icon angle. Or perhaps this. Yes. It'd be nice if I could draw my own icons for all of these, so that I could keep track of them more easily, because pictures of them aren't very descriptive. Especially not for giant amorphous masses like this thing. And then now I can attach them to each other horizontally to form the banks. There's a bank of 4 wide. That's 4 registers of 4 bits. One full 32-bit register. And appending 4 more should make this a 64-bit register. There. We actually want, I think it was 16 of these in parallel. So making another temporary. And then just appending this onto this. And now we have 16 of these, which is important because the maximum number of combinations in 4 bits is 16, so we can address all of these with a single 4-bit half byte. However, this is only going to be one block of the more modular system for holding memory. Remember, the sequential addressing, we're going to be able to need to append as many of these banks onto the addressing system as we want in order to make it infinitely extensible. I think it'll be somewhat like how the internet works with, you know, the URL codes. So technically, each one of these banks is going to have their own specific URL code in a giant bank network. And so this has become irrelevant. We don't need that anymore. This thing is soon to be irrelevant, since we're going to be replacing that with a real state machine. We're also going to need to devise the addressing system, which I actually feel is going to have its own state machine in order to process the addresses. Or perhaps an even more modular design. Each one of these banks is going to have its own sub-machine with its own address. And they would... Oh, I have an idea. Have them be docked to each other sequentially so that... yes. I'll explain what I mean later. Yeah, that is if I even get to it. It could just be a mystery. So now about you. This is going to be the hardest part because I don't actually know exactly what I'm going to do with this. I do know that I need a clock. Every computer needs a clock. And... remove that thing because it's redundant now. Oh yeah, I forgot to save this. Actually, there's something I need to do before I do that. And that is... there it is. Yes, this looks correct. And I can just dock this onto here like this. And then each one of these pins can go to its adjacent taker. Oh, that's not good. This isn't actually the part we need. I forgot. I actually need to use a splitter, because otherwise it's always going to be triggering one of these. And that's not correct. We want it only to trigger conditionally. So this thing... And we can put it on the same way as before, or perhaps this way. No. This way feels fine. Now the real difficulty is doing the wiring correctly in this cloud. There's a very thick fog of wires, and so it's easy to get distracted. However, I am a trained professional, so nothing to worry about. And so now, instead of these being red for special input, this one will need to be red for special input. And then these are also going to be turned black because they're also irrelevant now. There. And so now we can write to any one of these and then have one set for one bus for going in, So right here we can have this be here, and then that can propagate to every one of these now. And this is the part of the wiring that I never wanted to do. Look at this. You're going to need to wire each one of these pins to each corresponding pin on the same layer vertically. And so, this is what your life becomes now. Welcome to your new purgatory. And so I'm going to save this for being done in segments, so that we don't get burned out on it so easily. And then later on, going to need to have a selector here, the joiner. Actually, no, we don't have what I thought we had. So I'm just going to deal with that later. I'm going to need to stack this. This is... and then it needs to clamp onto there. And this needs to have the same input as that one. Actually... no. Yes, this is going to be a nightmare because of how many connections there are in parallel, you see. I'm going to need to wire each one of these yellow pins and each one of these blue pins to something. Fortunately, I've already completed this first layer, so we don't need to worry about that anymore. And that's that abstracted away. Now we just have the next 3 layers to worry about. You should be very thankful I chose 4 bits over 8 bits because it would have been twice as much wiring. No one wants to watch that. So, in regards to the state machine, as we were describing earlier, there needs to be a number of possible states, firstly. And for storing state, we need memory. I have a feeling we could store 16 possible states in this one 4-bit register, which would probably be enough states, or perhaps not, being very specific. And then after that, there needs to be some kind of conditional detector for branching between states. So some kind of ROM, which would need something like a decoder in order to function. And so, yes, and then attaching this to this. Or, just hypothetically for right now, we can do this. And so now, for each possible state we are in, we have one possible direction to go in. However, for conditional branching, that's not enough. We need multiple possibilities for multiple situations. Now, of course, we don't want this to constantly be on, so we'll probably need another splitter just like this one. This clock should be used for detecting, or no, for synchronizing detections and actions somehow. But how specifically is going to be a big question. And so now, instead of there being only 4 states that can only be cycled through in a specific order, we have 16 states that can be cycled between in a different order. Because we don't have branching yet, they still need to happen in a specific order. So, hypothesis. Perhaps we need a 5th pin, or just another decoder, for branching. Or perhaps some other process for altering the state conditionally. I'm going to take a break from thinking about that while I wire the next layer of these. So the problem then becomes we need a way of detecting a state in usually the accumulator, such as the regular ones like if 0 and if greater than or less than 0, or if negative or positive. The funny thing is, 0 is not a positive number, it is a non-value. It might as well be null. And simultaneously it is not negative. So that's layer 2 complete. So 0 here should be the starting state. And so the first thing it should do is start, it should immediately go to the boot sector in memory and start reading instructions from the bootstrapper, the piece of code that either loads an operating system or something similar. Now that's for booting computers. There are also other options. I think technically you can load a simple interactive programming language or just some kind of command prompt as an operating system from the boot loader, from the boot sector. The boot sector in memory, from my memory, almost always starts at 0 in memory, and if that's a corrupted sector in memory, it loads from the first possible sector. Since in reality that can be corrupted sectors, since, well, reality is not as perfect as theory. Yes, I think the first improvement we can make is what we already discussed with the splitter. And additionally, we'll need 2 of them. One for in case the condition is false, and one if it's true. And so this will be false, and this will be true, and this will be false. And the branch flags will determine which one of these is activated on clock cycle. And so, yes. Now we can make decisions based on information in the machine. That's progress. Now we need some kind of ROM. So a way of... Oh yeah, well, I know one way, technically. Hold on, this is going to get really bad. So, one thing I can simply do is have each one of these out pins for these branchers or selectors have a specific combination of bits selected here, so that when they're active, it sends a single value, which can then be routed directly back into the state, which will allow us to alter our state conditionally based on whatever and decided by us. And so that will be the hard-coded instruction set of the machine. Think of it like a condition set for a Turing tape reel machine. If condition A met, shift to state B. And these two are arbitrary, so they can fit anything. Yeah, and so it can have a special case in which if we are in state 3 and it detects a value greater than 5 in the accumulator, then it will branch to state 11, in which case it will add that value in the accumulator to itself to double it. Which, a funny detail is, doubling a number is easy, you just need to bit shift it. I feel like most most things that you would do with a computer are going to be very difficult on the metal layer, because in this case, for a 4-bit machine, with the largest single number you can operate on being 15, that's almost nothing, and so you would need to do arbitrary length arithmetic for almost every operation. And so moving to a higher level language is going to be a very high priority for us, because otherwise we're going to be stuck doing really boring menial tasks like calculating carries for addition every line. We're going to need to figure out things like functions and subroutines soon, and coroutines. Eventually we're going to need coroutines for multitasking, but that's nowhere near where we are right now. Multitasking in operating systems wasn't even invented, I think, until around late DOS. I mean MS-DOS, not IBM DOS. And I distinctly remember almost every operating system before that only being able to run a single program at a time. Very limiting. And so, from here, I don't like how this isn't on a board, though. It's going to make it difficult to work with. I don't like having things be free-floating anymore. I learned from the mistakes of the past. And so now, rerouting this. There. And so that's ready for expansion. There. And this can be redacted. Now, from here, we should be able to just clamp the clock onto anywhere in the machine. I don't like how it sends out that initial pulse like that. I feel like I'm going to need to fix that first. But before even that, I need to figure out a way of fixing it. So what I can do is put this on a plate also. The most awkward position to work with possible. Fortunately, it's easy to fix. There. And now from here I can route this and also actually, I don't like this clock design anymore. I feel like this is a better clock design. Yes. And so now this can be glued on anywhere. Now what was the name of this? Just clock. And so now we can also change this after we've installed it. There. I think this clock speed is much too fast, though, so we're going to need to find a way to reduce that. Trying to think. I know one way, but it's complicated. we could route this directly into a T flip-flop, which would then half the frequency, and then put that through another monostable, which would basically be this, but only half of the time. And so this would actually be routed into these two for the state machine. Wow, this is actually a much better design than anything I've made with something as crude as this. I don't ever want to see this again. It's disturbing. I didn't even need a sequencer. All I needed was this, this much more elegant model here. And now, I'm going to need to figure out how the branching is going to work specifically instead of just broadly. One thing I can do right now is, in the accumulator, install some flag detectors. Usually I like to have 3 flags, or even possibly 4. One flag for negative, another flag for positive, and one final flag for 0. So, which way does this go again? So this is the least significant. I see. And this is the most significant. And so I can color them accordingly. So, the first one will be 0. So if any of them are on, then it will not be on. So that's a NOR. And then the next one will be if positive. So for this one it's slightly more complicated. First, right now, if negative. If positive requires not if negative and not if 0. So that's just that's just the absence of the other 2 cases, literally. And so now there, it's not negative or positive, it's 0. And I should probably color code these as well. So this one will be gray for that one. This one will be dark red for negative. And this one will be not blue. Light blue for positive. That looks correct. Yes, I feel that's pretty indicative of what's happening here. And then I should probably put an extended marker on it just to keep track of all of this. Perhaps something like this. Yeah, that looks better. And then I can route these directly over here. And then... And that's where we run into this new wall. What do we do with them? Based on state, there should be states for detecting all of these flags, and then performing actions based on those. While we're thinking about this, we can wire a new layer, because it's been some time since we did the last one. There. I already have a very good feeling about this whole new paradigm. So the state machine concept works a lot better than the old control unit concept that I had before. This is much more flexible and is even reprogrammable if you're interested enough to alter the hardware. What would be even more interesting is one that uses an EEPROM, where you can electronically reprogram the ROM so that you can actually have a state machine that you can reprogram at any time, which I think is pretty great. Some may disagree. And regarding this thing, this is probably the most compact and efficient ALU I've ever designed, and certainly the most well thought out of all of them. I feel like I'm forgetting something somehow. Oh yeah, technically I can remove this entire abstraction layer because all of these are now wired. And so I could actually have this be one tick in latency faster. This entire operation. This entire system is perfect for pipelining, I feel. So, oh yes, of course, this will be the control signal out to the ALU, the state. So how many states do we have possible here? Again, 4, 6, 8, I think 12, which leaves an additional 4 for 16, which is the number possible. So we could use those additional states for branching and memory addressing. We have 3 possible flags, which would typically consume 3 possible states. However, there's another way to do that, and that's to detect if that flag is equal to something in memory, which would require only one state, a comparison operator, to compare what's in memory to what's in the accumulator. So something that's actually much more akin to higher level things. Or even better yet, comparing the first and second entries in the stack to each other. That would make things even more concise and efficient. And so we wouldn't actually need these 3 exported state flags, we would just need one exported state flag from the interaction between the accumulator itself and the top level of the stack below it. Although, technically this is the top of the stack, the stack that is to be, and is not currently to be. Quite perplexing, all of this. Needing to think in an entirely new way in order to get this to work, which is a good sign because that's a sign of advancement in technology, not knowing exactly what you're doing with it. And then of course we have this display, which I would actually like to improve. Temporary duplication. And appending these to each other and concatenizing. And part of that is getting under them. And so this will be more advanced already, once I'm done with it, that is. And that all looks correct. And so now this display is 8 digits wide, 2 digits tall, 8x4, I mean 2. And so, let me think. This is quaternary. Doing the math. 4 to the power of... That's 16. Oh, that's a very large number of, of the possible state. And so reducing this to hexadecimal, that's actually just chopping off the additional 8, and only regarding these 8 here. So that's 16 to the power of 8, which... trying to remember exactly what that is. So, I remember this is 256. Now this is... what is this? There's something like 65,000 or something close to that. And so these 6 digits here gets close to 65,000 in my memory. And then the rest of these, I'm sure you're aware, are going to be even bigger. And decompiling these down to binary, I can count through the powers of 2. So this is actually 32 bits. So that's the 32-bit integer limit. Oh yes, now I remember how very massive that is. I think that stretches into either the millions or billions. And that's the size of the number that can be held on this one display if all of the digits are to be one number together. However, I don't want to stop here. I want a much larger display. So that I can finally visualize all of my information. And then eventually we might want to look towards optimizing it so that it doesn't consume so much processing power that it lights the computer on fire. There. Oh, that's not good. I accidentally introduced a fault line. I'm just going to get rid of all of this. Because we don't want a screen like this. That is the opposite of ideal. And... it's so irritating to need to flip these upside down, I might as well just introduce a temporary clamp like this. There, and that also automatically aligns it so I don't need to worry about that. And problem solved. So this is the 64-bit integer limit now, because I just doubled it. So let me think. The pixel resolution, that would be 5 by 4, and the 5 is multiplied by 4, so that's 20 tall, 20 pixels tall, and the 4 is multiplied by 8, and so that would be 32 pixels wide, so 20 by 32. That seems like an awkward resolution. Reducing it, that would be 10 to 16, or 5 to 8. A 5 to 8 resolution. I have a feeling that's an uncommon resolution. So this is going to be the bare necessities for doing slightly higher level operations than just machine code. Although this still is only capable of displaying quaternary digits, not even control signs like parentheses or commas or brackets or even alphanumeric symbols like letters. Oh, you know, it'd be fun as if we invent our own alphabet that has its own symbols for every sound. That would be fun. Actually, don't I remember? No, this no longer is a problem now. Adding this actually resolved a huge problem in the design, so this clock is objectively better now. We didn't need a clock with as high a frequency as the last one. In fact, no one needed a clock like that. I guess, and eventually we can also make speakers for doing sounds. However, that's much later. And now we can also do screen space memory, so 1 register for every 2 digits. So that's 8 by 4, that's 32 registers? Yes. No, that's 16 registers. What made me think of 32? 8 times 8 is 64, so logically 4 times 8, that's 32. Oh wait. Yes, that is 32. I keep getting different numbers because I keep doing different math. Not ideal. I think getting rid of this build plate will help me think. It's been irritating me. There, now it's more open. More of an open floor plan. And so now we can actually move these 2 pieces together, closer, so that we can think about them more as being different modules to the same whole. And so we're building our extensible memory system, our extensible state machine system, and our ALU, which is not extensible. It just is what it is. X equals X. And so now, well, this doesn't really need to be that extensible yet. Eventually we might want to make ALU modules that act like different cores in the processor. That would be very interesting. We might even want to make some kind of GPU for handling the display. Now that could be also quite fun. Something that does hardware line draw things and box drawing and circles. Doing sine and cosine, I'm just now realizing, would be very difficult at this level. Yeah, any kind of trigonometry, really. Calculations for sine and cosine require very, very intensive operations, and they're not even algebraic. They're what's the word for that again? Converging. Yes, each step of the process brings you closer to the correct answer, and so there's a small divergence each time you perform sine or cosine. But as long as it's within the floating point, what is that also called? Floating point rounding, then it should be outside of the scope of necessity. Although that that error can also add up, floating point rounding, to give you logically incorrect results. And so it's actually preferable to keep something in its algebraic form for as long as possible before evaluating it. You don't want to do 1 divided by 3 initially, unless you need to. That's something you want to backlog for much later. And that's another problem, knowing when to backlog a problem for later, and when to front load it for now, to preload it. Today feels like a lot of progress. Getting much closer to the end result. Feels like the ALU here is almost entirely done. The control unit, I don't think is going to act like this anymore. I think it's going to act more like this. Wait. No, that's memory. What am I doing? Hold on. This all needs to be redrawn. Get rid of all of this trash. So, in essence now we have the ALU here at the core, and then the state machine out here, and there should also be the memory modules here. Yes, very good. And they should all be linked in series like this. And then that all connects to the ALU, which is connected to the state machine, but the state machine is also connected to the memory. And so technically, or wait, do we want this to be how this works? We could have it work like this, or we could have it be disconnected, and instead it only interfaces with the top of the memory system. And so this input only takes data, and this one only takes control. Or something that's infinitely more extensible is this. Everything is connected to one data bus, and that one data bus does everything. And as long as the state machine knows what it's doing, the system has integrity. And then later on we can also parallelize these ALU modules, although you can only push so much data through a single bus, so that also might need to be revised into multiple buses, like this. Sorry about that, minor distraction. No, not like that. Like this. Oh, okay. That also renders this incorrect. And so, kind of difficult to display in 2 dimensions, but it looks more like this, where we have multiple data buses, and so we can transfer more information at a time, which helps with parallelizing like this. And then we need... eventually I feel like we're going to need something like a GPU, so actually tear this off of the top like that, and raise it, and extend these. And the interface I'm just going to put here, instead of directly interfacing with screen space memory and the inputs, well, probably have the inputs be, no, not that color, this color, and just there, and then that can be, well, that would interrupt the data bus, so yes, we need some kind of input handler, some I/O handler here that will control both the input and output. So that can be a cross between a GPU and a hardware input driver. And so this can be the out here, and this can be the in here. And then both of these can be controlled by this system here. I'm not sure how this unified system would work. I think it would probably actually be better to have well, I'm going to leave it like this for right now. I don't want to dig too deeply into it yet. But this is starting to look much better than before.